Hi everybody, I'm going to go over ozonolysis in this video. So this is a neat little reaction that you can essentially think about it as like molecular scissors. Okay, we're literally going to be chopping bonds apart, which is definitely kind of a unique thing about this. Carbon-carbon bonds are not exactly the easiest things to chop, but as you see the things that I've drawn here, they chop carbon. So I don't have any oxygens or anything in here. So this is definitely an interesting reaction because we just are going to be chopping those sigma bonds to bits. So this is a good way of taking alkenes, turning them into aldehydes, carboxylic acids, ketones, and you can also do this with alkynes into carboxylic acids. So definitely kind of an interesting thing. We first need to talk about ozone a little bit. So ozone is O3, okay? So if we think about O3 in a neutral way, you know, we've got 3 oxygen atoms in a row, and then how many electrons are in between them? We have to make it neutral because I did not put any charge on that O3. So let's say that I want to first make the one on the left neutral. That means that this oxygen now has a positive charge. This one would have a negative charge. So that's the structure of ozone. Obviously, you've got electron delocalization, so you've got a resonance structure that you can draw here. So we do have some delocalization there, but that is the structure of ozone that we're going to be working with. So the first step in all of these is going to be ozone. Okay, and then it's really the second step in terms of how you're going to kind of break down one of the intermediates that's formed after the ozone in terms of what exactly your final products are going to be. So if you do reductive conditions, then we could use zinc and water, or, and I should have switched these, switch them right now. Or we can use dimethyl sulfide, which is just as fun as it sounds. So we've got 2 options for reductive conditions. So both of those are going to give us aldehydes and ketones, okay? Okay, so we're gonna get aldehydes and ketones out of both of these. So I'm gonna go over the mechanism, but I'm gonna kind of show you the little cheater way of how I draw the products first. Because this mechanism, I will show parts of it to you, but it is definitely a little bit complicated. We'll be talking about the type of reaction or mechanism that it goes through a little bit more later in the semester. But for right now, I just want you to kind of know the little shortcut trick. So when I'm talking about molecular scissors, you can be very, very literal with that, okay? So the way that I think is the best to draw these products out is we are literally going to get our eraser out, make it nice and small, and we're just gonna erase, oh no, make it partial. We're gonna erase part of that alkene, okay? The products of these reactions, they're literally that, okay? If I just put an oxygen on each end of that. So I can draw that a little bit more cleanly. Let's just scooch that away a little bit. That is the product of that reaction. It is that simple, okay? So the ozonolysis, it really just cleaves right through that alkene with the pi bond and the sigma bond, and then turns those two carbons into carbonyls, okay? So if we number out our atoms here, 1, 2, 3, 4, 5, 6, we still have all of our carbons, except do that the same way. 1, 2, 3, 4, 5, and 6. If we do that on the other side here, so let's do the same thing. We're gonna just erase right down the middle there. Just because I'm trying to make a video where it's clear, I'm gonna scooch that away a little bit. Oxygen, oxygen, that is my product. So keep in mind I have H's here. So this is how we're making the aldehydes, we're making the ketones, and it just depends on what substitution you have on your alkene to start with, right? Nothing changed. But again, we have the same instance where we've got 1, 2, 3, 4, 1, 2, 3, 4, okay? So this is actually kind of a neat way of, if you just have too many carbons, you can just chop one off, throw it away, because you can imagine that if I have a really big molecule over here and I just have formic acid on the other side, that's just going to come off on the rotovap. So you can just kind of say like, well, that's gone now. I don't have that because it's like just evaporated away. But with doing reductive conditions using zinc and water or dimethyl sulfide as your kind of second workup step, you're going to end up getting out your aldehydes as products. Okay. So we can also do ozonolysis with oxidative workup. So this would be oxidative conditions. So if I add hydrogen peroxide as a second step, that's how we're going to get out our carboxylic acids. Okay. So again, I'm going to do the same process though. Just going to copy that over. We're going to eat away. Just make eraser noises here. I'm going to zoom in so I can make little O's. O, O. Okay. And it's fine if you draw a stupid one first and then redraw it looking a little bit nicer. That's what I'm going to do for this one. This one's not so easy to just move things without breaking other bonds. So it's important to keep in mind that I didn't break that bond. I didn't break these ones. So the only thing that broke is my alkene right there. So this is still going to be one product in the end, right? It's just instead of the two products that we saw previously, because it was already in a ring, it's just now going to be a linear molecule. Okay, so let's do ourselves a favor here and do some numbering. Okay, so all of that is still intact. And if I was going to redraw it to look not so silly, let's go ahead and just one, two, three, four, five, 1, 2, 3, 4, 5. Okay, and then we need to deal with the fact that it is in oxidative conditions, which I almost forgot about. And then instead of having this H here at carbon 5, so it was an H, we're going to make that aldehyde, and then it's going to get oxidized by the hydrogen peroxide to the carboxylic acid, okay? So let's number this out, 1, 2, 3, 4, 5, and then just do a quick double check. 1 is a methyl, yes. 2 is my ketone, 3 is a CH2, 4 is a CH2, 5 is a carboxylic acid. So that's correct, okay? but I would recommend doing this version first rather than trying to just go straight to this where you've gotten it nicely drawn, okay? But that's how you can make ketones and carboxylic acids. Okay, so any alkene that started with a carbon there is going to give you a ketone. If it's got an H there, it could either be an aldehyde or a carboxylic acid, depending on the second step of the conditions, okay? All right, and then the final one is with alkynes. So alkynes are kind of interesting because we only have one set of conditions for these. So we're gonna finish it up with water. So because we already have an extra pi bond there, you're pretty much always gonna go to the carboxylic acid. I'm gonna scooch things over real quick. There we go. Just on the edge of the iPad here. Okay, so we're pretty much always gonna get the carboxylic acid. So the way that this is going to work is we can do essentially the same copy paste process. It's going to look slightly different though. So we can definitely squeegee out our middle bit here, but we're also going to need to take care of one of those pi bonds. So we're not making a triple bond to oxygen here. We're not doing anything like that. But we are going to be making carboxylic acids. Okay, so you can start off with the kind of crazy drawing first and then adapt it to something that looks a little bit more normal. But again, we're not deleting any of the carbons. They're all still present. Okay, but we have, I made that orange. But we've got carboxylic acids out here. Let's just add some numbers real fast. That's why I had the orange. Okay, so we still have all the carbons, but the carbons that were part of the alkyne have now turned into carboxylic acids. Okay, so this is the part that I really want you to know, is just kind of what ozonolysis does. The mechanism, like I said earlier, is a little bit complicated. We're going to go through the main part of it that actually uses the ozone, because that's when you essentially form the oxygen carbon bonds, which are giving you your products. And you're also seeing how the carbon-carbon bond gets broken. Okay, so the mechanism is actually a 1,3 dipolar cycloaddition. And cycloadditions are part of a class of reactions called pericyclic reactions, where you essentially have complete electrons delocalized in a circle as a transition state, and there are no intermediates. So it's a single reaction process. So the interesting thing about these, there's a whole class of them. We'll be talking about some cycloadditions later on, as well as some other pericyclic reactions later on towards the end of the semester. I think they're a ton of fun. They have really neat, like, fun orbitals associated with them. And so I'm excited about it, but we're gonna go kind of like dipolar cycloaddition light here. So let's just show it on, let's do this guy. I think that'll be reasonable. Yeah. Is that it? Yes, okay. So we're gonna do the reaction on this. So we're gonna use our ozone. This is gonna be our first step. And the thing to keep in mind here, a 1,3 dipolar, this is a 1,3 dipole, okay? Because you can go 1, 2, 3, and you've got a dipole. That's as complicated as it needs to be. So the whole thing about pericyclic reactions is we're looking for electrons moving in a circle and in a single step, okay? So what we're gonna see here is it doesn't matter which way you draw these arrows, but I tend to like to think about it, especially with the dipolar ones. Not all of the pericyclic reactions have dipoles, but for the dipolar ones, I like to start with the negative charge. So we're going to start with the negative charge attacking that alkene. Those pi electrons in the alkene have to move somewhere. So they're going to move over to this oxygen. And then we can have electrons move on to the oxygen that is positively charged. So if we look at the transition state here, okay, so I added an extra dotted line here. So this sigma bond was persistent the whole time, but I added a little dotted line there because we want to think about the fact that we still have this resonance structure. So I have a partial bond, a partial double bond between the oxygens on both sides. So that's why I added this one. But the key point of a cycloaddition reaction or any pericyclic is that you've got that dotted line of electrons in a full circle around the system that's that is seeing the reaction occur. So that is my transition state. You don't really need to know that too much, but there it is. So if we follow those electrons to see what we actually got out or what we actually did, I'm going to draw it down here. Okay, that's probably, okay, I'm going to fix the transition state so that it's on the other side and not looking as dumb. Okay, I got it fixed so that my bond angles are not insane anymore. Okay, so now this is I think it's a malazonide or something like that. The names for this are kind of crazy. But now you see we've added some carbon oxygen bonds. We've gotten rid of the pi bond because we had to use that in the reaction. So then the next step is actually a reverse of what we just did. So it's a retro 1,3 dipolar cycloaddition because we're going back to a dipole and the other cycloaddition piece. So we're not going to break the bonds exactly where we formed them. We're going to kind of do it a slightly offset version. So this is where we're going to see that sigma bond is going to get broken. And part of the thing that drives this is the fact that all of these oxygen-oxygen bonds are weak, just like we saw in the epoxidation reaction. We're seeing those weak oxygen-oxygen bonds. Okay. Now I gotta. No, sorry. I need to start from the lone pairs. That'll work. Okay, so I need to use these lone pairs. There we go. So that's going to be my retro version. It just took me a while to get the right places. All right, and then that's going to give us that aldehyde and another dipole. Okay, so again, we have a situation where we can have resonance. So we can have it delocalized between an oxygen and a carbon in this case. So if that thing breaks apart, you can imagine if this piece just flipped, then we'd end up getting, then we could do the reaction all over again. So it's like a forward dipolar cycloaddition and then a retro dipolar cycloaddition and then another forward. So we're going to do a flip of the aldehyde. Okay, so literally just flipped it. I didn't do anything else. And then we can see, again, that forward dipolar cycloaddition, where we're going to do the same 3 arrows in a circle. Oops. That's going to give us another 5-membered ring. And now at least we don't have as many of those oxygen-oxygen bonds here. And so this is an ozonide. And that is the thing that is at the end of the O3 process. And then you'd add in your various, your zinc and water or your dimethyl sulfide or just water or whatever. And then that's when you would get the carboxylic acid or the ketone, the aldehyde, any of those things, okay? So this is where you put in your zinc and water. Okay, so you'd put any of those and get out your products. Okay, those second step reactions are also very strange mechanisms. So I figured this would be a good one to preview, but the next steps are kind of outside of the bounds of this class, I would say. But that hopefully just kind of helps you see how some of those bonds get broken. And once we get to the ozonide, you're not breaking carbon-carbon bonds anymore. You're only breaking carbon-oxygen bonds, which is much, much easier to do. But this way you can at least see how the dipolar cycloaddition works and how we get essentially that chopping of the alkenes. But if you don't want to think about the mechanism at all, that's fine. It is kind of a complicated one, but we will be seeing this again later in the semester, but just keep this part in mind with the molecular scissors. We're just like chopping that, adding oxygens in. All right, so hopefully this was helpful. Again, let me know if you've got any questions and I will see you all later.